much. Thank you for the previous presentations, Cindy and Lynn. Learned a lot. This is not the kind of usual presentations that I sent them, so always good to hear about what other people are doing. And also thanks to Chi and everyone else from COMET for inviting me to give this presentation. I'm pretty chuffed to be here. So my name is Samantha Engwell, and I am a senior scientist at the British Geological Survey. And I'm going to have the same issue. No, okay, cool. And so I thought I'd start off with a bit of a career overview. And so this slide essentially is what you would usually find in a CV, and is actually pretty much copy and pasted from my CV, providing information on, you know, my history in terms of education and research roles. So going from my undergraduate through to a master's by research, similar, it sounds like, to the one that Cindy did, a PhD in volcanology, where I essentially looked at ash dispersion and uncertainties in deposits, through to more applied research roles, and eventually winding up in my role as senior scientist that I've been in for about 3 years now. And it's really easy to see these sorts of CVs and this information at face value, but I wanted to give you a bit of a kind of like behind the scenes of some of the decision making and parts of my career, the decision making parts of my career behind these. So after my degree in geology, I didn't really know what I wanted to do. And I took a summer role at the Edinburgh Microprobe facility, and spent 3 months researching epoxy resins. If anyone works with epoxy resins, they'll know how exciting that was. But in all seriousness, it was amazing. And I realized that research was something that I really enjoyed, like really getting to the bottom of interesting problems and really spending time to think about solving problems was something that I really loved. And so moving on from that, I did a master's by research. This was in natural hazards, and it allowed me to kind of have some insight into different hazards, and then further focus onto what I wanted to do later in my career. But I wanted to mention this because this is really, this master's and some of the outcomes of this master's probably one of the main regrets of my career so far, in that my master's was essentially, what I did was produce a thesis on how not to do something. So my science question was around simulating lahars on a volcano in Colombia. And essentially I spent a year showing all the ways not to do that. And that was because of issues with data, with issues to numerical modeling. But my regret around that relates to the fact that I never published that research, because I felt like, to me, that was a failure because I didn't have this amazing result. I hadn't solved the problem. But one of the reasons why I still think about that now is that often I see people give presentations, particularly students, around similar things, and they're coming across very similar issues. And I think that we need to get better at presenting kind of null results and negative data to really help move science forward and stop people repeating similar mistakes. So that's just a kind of insight into some research that I did. Following on from my PhD, I wasn't sure whether I wanted to go into academia or industry. And I chose a role in academia because it was specifically a kind of training role, which allowed me to learn numerical models, and in particular how to make my own. And I took that role because I felt like that allowed me, even if I didn't then want to proceed into academia, that allowed me to give me skills that would still allow me to progress in industry as well. Following on from that role, I was looking at other research positions. I had applied for many kind of fellowships and things, that unsuccessfully, as is often the case. And then towards the end of my position, was offered both postdocs and my permanent position at the BGS. And in the end, I took the position at the BGS. Obviously, it's a great opportunity and it's a great institution to work for, but also balancing my kind of personal life, right? So thinking about what I wanted for myself outside of work going into the future, and having this role allows me to be close to my family and prioritize some of my things that are more interesting for me personally. So moving on to some of the things that I do within my role at BGS. So my role is both research and I have more applied roles. So here's just a couple of examples of research projects. So I still apply for example, NERC research projects and research grants. And recent grants have been around the Anak 2018 eruption and the Krakatau 1883 flows. And these projects have involved going into the field, looking at deposits, trying to understand deposits and what they mean in terms of eruption processes. And all of this has been in collaboration with both colleagues across UK and further afield, but in particular with colleagues in Indonesia. And I definitely say that my career has really benefited from the different collaborations that I have been able to make throughout my career to date. Another example of that is this image on the right-hand side, which is a screenshot of some pyroclastic density current numerical simulations from the 1883 eruptions. We've got Anak in the middle and the PDCs are propagating away. And this was from a numerical model that I produced with colleagues at INGV Pisa. And similar to the last presentation, thinking about the formation of tsunamis related to this, in this case, this eruption. So I mentioned that my role incorporates both research and more applied work. And in terms of the applied work, a lot of that is around formal advice. So BGS has a number of roles in which we give information to, for example, the UK government, to EU civil protection. And this is a particular role that I lead on, which is around ash and aviation. And so I work with the WMO and the ICAO as part of what is called the Advisory Group for Volcanic Science Applications. And essentially that's a group of 8 experts from around the world who are either in research or operational institutions. And our goal is to really pull state-of-the-art science through from research into operations. And what do I mean by operations? So here we're talking about ash and ash hazard to civil aviation. And in terms of quantifying that, we have global airspace is split up into 9 different regions, each which is controlled or has a responsible volcanic ash advisory centre. The role of that Volcanic Ash Advisory Centre is to provide information to civil aviation in the event of a volcanic eruption. And how they do that is they decide on parameters that describe the eruption. So for example, a plume height, they use that to initiate a numerical model that simulates and forecasts where ash will be at certain times in the future. And then they produce products like these. So this is, again, looking down, in this case on Kalut volcano. And here we can see polygons that essentially delineate where ash will be at certain times after the event. And so essentially what they do is they define parameters, they apply their numerical simulations, and then they produce these products. But obviously, all of, like any numerical modeling, all of the outputs are really dependent on the quality of the inputs. And that is where my research comes in. So I lead something called the Eruption Source Parameter Database. I've put the QR code up here so you can peruse at your leisure. But essentially this is a website that contains eruption source parameter information for every volcano that's been active within the Holocene. This was originally put together by the USGS in 2009, and it's something that we now host and I update essentially based on what volcanoes are doing or have done since then. And so on this slide, what I wanted to highlight is that all of our advisory roles are underpinned by research. So this is a lot of research that goes into informing this data set. And this is one of the resources that we provide and I work on to provide eruption source parameter information for initiation of those numerical models that I mentioned previously. I also work a lot on understanding and communicating the sources of information in these input parameters, these source parameters. And here's where I want to talk. Here's what I want to talk to you about for the rest of the presentation. There are so many difficulties associated with inconsistencies in data, and in particular in the published record, that make things producing data sets and databases like this really difficult. And I think that there are some very simple solutions that we can apply that would make these things a little bit easier. So just so we're not all on the same page, and so I can give you some pictures of volcanoes. So here are a couple of examples of volcanic plumes, one from Japan in 2011 and one from a very famous eruption from Pinatubo in 1991. And you can see that they have very different shapes. So we have a bent over plume as the plume is affected by the wind on the left-hand side, and a developing umbrella cloud on the right-hand side as the plume starts to spread radially in the atmosphere. And this is one of the sources of uncertainties in terms of identifying things like plume height, which is what I'm going to talk to you about for the rest of the presentation. And plume height is perhaps one of my favorite things. It's one of the key input parameters. It's one of the parameters that numerical models are most sensitive to. And it's also one of the parameters that we have a lot of data on in various places in the record. So kind of a philosophical question, and I'm asking this because I'm kind of aware that there might be lots of different people in the audience that maybe are looking at plumes from different viewpoints. But what do we mean by plume height? And this really gets to the crux of the problem, in that if someone's looking at a plume, a volcanic plume in front of them, what they quantify or what they measure as plume height might be very different. And that's because in the published record, we have lots of different measures of plume height. We have a maximum plume height, we have a maximum spreading height, neutral buoyancy height, bottom spreading height. And essentially for operational response to volcanic eruptions, what we want to know is at what height is this plume spreading at. And so it's really important to be able to distinguish the different plume heights in the data. The other aspect, the other kind of issue that affects certainty around what we mean in terms of plume height is related to how it's measured. And there are lots of different techniques that are employed. So many of you will be familiar, I think, with satellite imagery of volcanic plumes, so looking down and using things like brightness temperature to estimate volcanic plume height. Here's where I spend most of my life, in looking at volcanic deposits, sieving deposits, and looking at grain size, and using empirical relations applied to that data to then inform estimates of grain size. And then we have kind of just direct observations of plumes and plume height. And the issue with all of these is that we could all be looking at the same eruption, the same plume, but we're using slightly different techniques and measuring slightly different parts of the plume, which means that the measurements that we might be getting can be very, very different. And so here just a list of some of the discrepancies that are related to estimating information about plume heights. Plumes are often very complex. There's often multiple plumes, for example, ash and SO2, and at different spreading heights. So Hunga Tonga eruption was a really great example of this. We had the plume spreading at multiple different levels. There's also issues with measuring different parts of the plume. So as I mentioned before, some people are presenting information around plume top, some people are presenting the spreading height. And again, the Hunga Tonga eruption is a really great example about the issues and discrepancies there. So there's 20 kilometers in difference between those two plume heights. When we're numerically simulating volcanic plumes, the meteorological conditions, in particular the wind direction at those two heights, may be very different. And therefore, if we get that plume height wrong, it potentially has a very big impact on our forecast for where ash is going. We also might be measuring either different parts of the plume or measuring parts of the same plume, but in different time space kind of areas, which means that we might not be producing quite the same information. And we also have, and that's before we even think about uncertainties related to measurement type, which there are so many. There are implications. So I realize that a lot of these things might sound quite trivial, but there are quite significant implications to not being able to use plume height information to the best that we can. And this is an example. So we often use plume height to understand the mass eruption rate of an eruption. So we quantify that using an empirical relation. And we assign that, determine that empirical relation based on past eruptive activity. And so here on this plot, we have all of the points represent one eruption. and we're plotting the observed plume top, so that's the very top of the plume, versus mass eruption rate for each of these eruptions. And from that, we can then fit a relation to that data and define an empirical relation. And that means that then if an eruption happens somewhere, we can use the observed plume height to estimate the mass eruption rate. On the right-hand side, we have a number of these different empirical relations. The grey one in the back is the one that relates to the plot on the left-hand side. But here, this is plotted for, the empirical relations are plotted for lots of different data, whether that's the top height, the spreading height, the SO2 height, the isopleth height, which is the height that's determined from looking at the deposits. And what we can see is, particularly for larger eruptions, there's really big discrepancies in this relationship. And so this just really highlights the importance of being really careful about understanding what measurement we're actually using when we're trying to apply empirical relations like this. So what can we do? So really getting to the crux of it is just, there are simple things that we can do in terms of how we record and publish our data. And a lot of it's around metadata. So how was the plume height measured and what were the assumptions? What part of the plume was measured? Was this the top, the spreading plume, close to the volcano, further away? What time does the measurement relate to? Was the plume height, and I laugh a little bit about this, but it's something that's really simple. Was the plume height above volcano or sea level? And if you can imagine, if you're thinking about a 2-kilometre plume from a 4-kilometre high volcano, that produces quite a big issue. And then what are the uncertainties? And then finally, also to talk to our colleagues. So some of the issues related to this problem are simply that we, as communities, tend to kind of work on our own little bubbles. And so geologists work on deposits, people, meteorologists work in the atmosphere, and sometimes there's not enough communication between the two, and that leads to miscommunication. And if we start to have these conversations about what the data means, what we need, then that really will help to kind of progress some of these science issues. I also wanted to say at this point that I've presented here around plume height, which is obviously very specific, but I think a lot of the issues that I raised around data is relevant to probably all geological and observational data. And so it might just be interesting to think about whether some of the issues kind of raised here are also relevant to some of your areas as well. And that was all I had to say. I hope I've kept to time. My email's there if you have any questions.